Imagine floating in the vacuum of space, right next to a blinding pillar of pure light. What happens if an astronaut steps out and tries to put their weight on it? Down on Earth, standing on a surface requires physical resistance. You push down on the floor, and the mass of the floor pushes back. But light is entirely massless. There are no atoms or molecules to support your boots. Yet physics dictates that light does exert a physical force. Even though individual photons lack mass, they carry kinetic energy. When a photon strikes a surface and bounces off, it transfers a precise directional momentum to that object. A single photon barely registers, but scale that up to a continuous stream of light. And those microscopic impacts accumulate into a steady, measurable push. Physicists call this force radiation pressure. So light absolutely pushes. The real engineering problem isn't whether the beam has force. It's whether we can generate enough radiation pressure to counteract gravity before the energy involved destroys the human body. On Earth, the push of sunlight is completely drowned out by the friction of our atmosphere. But in the vacuum of space, radiation pressure from a star accumulates into an incredibly powerful force. It is powerful enough that astrophysicists have designed theoretical megastructures called shot-off thrusters to literally steer our entire solar system through the galaxy. The thruster functions as a giant parabolic mirror. It doesn't orbit the sun instead. As vast amounts of solar radiation hit the mirror, the pressure from those bouncing photons physically props the structure up, slowly pushing the star in the opposite direction. Over millions of years, this radiation pressure can relocate a star and all its planets. Because light can move a solar system, the physics required to support a human on a light bridge are completely valid. We just have to scale the mechanics down. Space engineers are already applying this exact principle to human-made spacecraft. By deploying large, highly reflective sheets in a vacuum, we create light sails. Instead of weighing a craft down with heavy chemical rockets, we can point a high-powered laser at the sail. The constant stream of bouncing photons provides a continuous, physical push, accelerating the ship deeper into space. This diagram shows the radiation pressure required on a human scale to hold a 70-kilogram mass. A gentle beam must compress into a hyper-focused laser. The required photon density graph shows that to generate lift, light intensity spikes exponentially to off-the-chart levels. To get enough physical lift from something completely massless, you would have to capture the raw radiative output of a star and concentrate it into a space the size of a human footprint. This brings us to the fatal flaw in our architecture. Photons do not cleanly transfer kinetic momentum in isolation. When light hits an object, it also transfers extreme thermal energy. The space industry is actively planning to use this thermal energy transfer to clear the millions of pieces of high-speed space junk currently orbiting Earth. The technique is called laser ablation. When we shoot a highly concentrated laser at a piece of debris, it doesn't gently push the target. Instead, the intense heat instantly boils the material, flashing it into vapor. That sudden expansion of gas acts like a localized explosion, releasing enough energy to punch a hole straight through solid metal. Physical matter cannot withstand that extreme energy transfer. The target vaporizes entirely, long before the kinetic momentum of the light accumulates enough force to physically support it. Which brings us back to our astronaut, hovering above a beam of light, mathematically engineered to hold 70 kilograms. This chart compares the two forces at play. The kinetic push rises slowly, but the thermal heat curve spikes instantly. The beam's temperature violently crosses the biological survival limit, a fraction of a second before the light provides any physical lift. At the exact moment the astronaut makes contact, their boot never actually rests on the light. The material undergoes instant laser ablation, rapidly expanding and vaporizing in a brilliant flash of plasma. Light exerts a very real physical force, one capable of propelling spacecraft and steering galaxies. But the extreme thermodynamics required to concentrate that force make it an earthly destroyer, a physical barrier that can never be tamed into human architecture.